Ok, pode botar. Okay, we'll start with the situation that we're going to consider. Will be a surface in the product space of two-dimensional Riemann manifold of Gaussian curvature K. It will be a sphere or hyperbolic space. In this, we'll denote by xi this unit vector of the factor of the R factor. And then we choose the positive orthonormal frame, which is first an adapted frame. It means that the normal vector is the last one, E3, and the two first ones belong to the tangent space to the surface. And next, please. Next, please. Yeah. And the E1 and 2 belong to the tangent space, and E1 is chosen so that it is the projection of the unit vector of the xi on the tangent space. I will define theta by the angle theta by the projection, by the angle with the normal, with the xi. And then the xi gets this expression, sine theta E1 cosine theta E3. With E2, E1, E2, this frame is well defined practically everywhere where sinus theta is non-zero. It will be called the canonical frame. It's very convenient because we are treating mostly on the surface of a constant mean curvature. And they are analytic. Since they are analytic, that function theta is analytic. And so it is only zero in a very small set. Actually a set which is a closed set without interior points. So it's defined almost everywhere. It's almost a global frame for that situation. We might have to use the Gauss equation, but probably not. That's the form with the theta, where K will always be the Gaussian curvature, the big K, and the H, the mean curvature of the surface sigma. Next, please. Okay. That space, that product space has appeared recently in various contexts. I will mention one of them, but one, probably the most interesting one, is the fact that it was the first space in which a non-trivial generalization of Hopf's term constant mean curvature was achieved. I mean, Hopf's term, it was only known for R3, S3, and hyperbolic space. And now there was a breakthrough when people found a quadratic form. The Hopf's basic trick was to look at a complex quadratic form that was holomorphic when H was constant. And then Abish and Rosenberg introduced that form of K2 in the tangent space where alpha is the second fundamental form of the surface, x, y are tangent vectors, and that K is the Gaussian curvature of the factor, two-dimensional factor. Then if you take isothermal parameters and the corresponding complex parameter and write that thing in this complex parameter, you get a form in dz and dz bar. And the part in dz square is globally defined. I mean, with that if we change the complex parameter, it will change like a quadratic form. And this is called the Abish-Rosenberg quadratic form, and generalize the Hopf form on constant mean curvature in the following sense. That's the basic fact. If H is constant, then that form, that quadratic form, is holomorphic. For the time being, I will not go into that. And some application of our term will be I'll come back to this quadratic form. But then the results we are going to talk about is, first one is the result with the Tribus and Alencar, I already mentioned. You have this surface, immersed, orientable, complete immersed surface with H constant, non-zero. assume the canonical frame, and we have in that canonical frame that it diagonalizes the second fundamental form, that alpha d1, e2 is 0. That's equivalent to say that the projection of the E1 is the projection of C on the tangent space. And this condition is equivalent to saying that this projection is the principal direction. So the normal one is again the principal direction, and then it diagonalizes the second fundamental form. Then there is something missing in between. Yeah, okay. Then sigma will be invariant under one parameter group of isometry that fixes an axis parallel to this direction, fixed direction in the space, sheet, and passes through a point P0 of this first factor, mk2. When k is positive, that means this is a sphere, these isometries are just rotations around the P0 point whose trajectories are circles. If k is negative, the situation is richer, much richer. You have that the isometers are all this one parameter group of isometers of the hyperbolic space. There will be elliptic, parabolic, or hyperbolic, depending on the nature of the trajectories. That's next. Please, you see this in the hyperbolic space. You may have geodesic circles and radial geodesics. Geodesic circles have geodesic distance constant, and by Gauss lemma they are perpendicular to the radial geodesics. And this is elliptic rotation. This is called an elliptic isometry. In the case of that fixed point comes to there's one point at infinity, there will be these circles become whole cycles, and again we have this whole cycle and the geodesic, the radial geodesic. Again, this is the family of orthogonal trajectories. And this is called parabolic isometries, the trajectories of parabolic isometries. And in the last case, you have two fixed points. There was one fixed point in the interior, there was one fixed point at infinity, and two fixed points at infinity. This is this stronger line is the geodesic, and the other lighter line are distance, just like replace that center of the circle by a line, and taking, instead of the equidistant circle, take equidistant curves. It's just a generalization of the first thing. It's called the hyperbolic isometry. So it will be one of these three one-parameter groups of things, and the rotation in the case of so this will be one of this surface. All will be in this category. They are always okay. Next, please. This theorem I'm not going to talk about it, so might as well omit it. Otherwise, if I have time, I'll come back to it. Okay. Then I'll make a very short, I say there, a sketch of the proof of that term, but I should have said this very short sketch proof of the theorem. From now on, I will use alpha ij to denote alpha in this canonical frame. And that distinguishes there, down there is a okay, yeah. Yeah, so that's the fundamental equation, yeah? This, It means that if the hypothesis be alpha 1, 2 equals 0, and that implies that this theta, that's a computation, applied to E2 is identically 0. In other words, the angle theta is constant along the trajectories of E2. That is a basic fact. Theta is constant along these trajectories of E2, but that is also constant. From now on, our trajectory of E2 will be called C. There's a notation. And there are other things that are constant along these trajectories. Alpha 2, this D2E2 is certainly a multiple of V1. This is the derivative, the tangent derivative, the component of the covariant derivative, the big space projected on the tangent space of the surface. And this B is constant along the trajectory of V2. And the alpha to 2 are also constant. This is the basic fact that were obtained by some number of computations which are not even mentioned. And from this, we can do this. Now embed the M2K into I3 as an umbilical hypersurface. So it will be a sphere or hyperbolic space in the sphere is embedded in the Euclidean space. Hyperbolic space is embedded in Lorentzian space. And then in this case, I have this particle embedded in R4 with some metric, with either Lorentzian or Riemannian metric or Euclidean metric. And then we can prove this fact that this curve C, the trajectories of E2, are contained in parallel planes in this R4. These planes are orthogonal to this fixed direction, 60, and the C are the intersections of P with the surface. We take the connection of the R4, the big space, call them D bar, and then we can prove this. That the D bar of E2 in the direction of E2, they have three components, but this will be perpendicular to E2. This will be E1, E3, and the direction, the umbilical direction of the surface within the ambient space. I call it this normal eta, and of course the coefficient will be the curvature of the space. And then compute this value. This will be B, will be cotangent alpha to 2. And then we want to compute the Jordan's curvature of the curve C, not in the big space, but in the ambient space, NMK. But I have to project E1 on this space, and the E3, they don't belong to this space. I have to project them, compute this projection, and then take the square of this thing, make some computations, obtain at the end of the computation that the Jordan's curvature is inverse of sine minus inverse of sine multiplied by alpha 2. So this will say when the thing is, let's assume in some case that k equal -1, that's it. The interesting case is the hyperbolic case. And then see if it is curvature is once a whole cycle, it's greater than one the circle, it is more than one the hypercycle. That will be used. Okay. Then we can next please. Okay. No. Where is it? Now I want to prove now the theorem. We can. Okay. To prove now the theorem, I have to prove several things, which I only sketch very rapidly. First of all, I have to prove that we haven't distinguished that all these curves are in parallel plane. So my surface is foliated by either circle whole cycles or hypercycle, the foliation of that. Then I have to prove, first of all, that these circles have the same center. So this is a rotation, yeah? The way to do that is, I have to be very sketchy on these things, but I introduce the height function. I have this direction xc, and then I introduce the function h, height function, that's defined at the point P of the surface, as the position vector times c. So what I prove first, I want to prove first that all circles have the same center. For the case of circle, I will treat the whole cycle case and the hypercycle case afterwards. And to do that, I show first that this trajectory of E1 are the gradient lines of the function of the height function. And then the E2, this will be the trajectory of E1, and then you have E2, will be the level surface of the height function. And from that I project all this circle on one of these parallel planes. I choose one of these parallel planes and take the circles of the surface that foliated my surface and project it down on this fixed plane. And then I have to prove that they are all on the same, all the projections are the same. It's some computation that can be done. Then I have to, now this is okay with the circle because I have an axis. Yeah, actually I could, the way I do it, I first show that locally this is so, and then I have to take the limit, and the limit of a circle with the same center is a circle with the same center. Yeah. Because you may have to take limits in this case. By the reason that that figure before that, because the crucial point is that could it be put a little bit below the, yeah, this projection, the submersion, restricted to the surface too, except at the point where cosinus theta is 0. That's where the tangent space contains the direction xc. If this happens, but this only happens because cosinus theta is an analytic function. I have constant mean curvature. So they can only be 0 in a closed set with no interior points. It's a very small set. But then there will be a large part of the surface which is not 0. Take a point there and show that all these things are circles. All whole circles, all hypercircles. And the limit due to be again things of the same nature. Because the limit of a whole cycle cannot be a hypercycle of a circle. And no limit of these three things can be one of the other things. Well, I said that was going to be very sketchy, and it is. I mean, something very sketchy, this proof. But then it can be shown and give a proof of theorem 1 that the surface, a rotation surface, one of these, in the sphere, only circles, in the hyperbolic space, one of these three types. Actually, these are all rotation surfaces if we consider rotation surface in the definition that was given by Baisha and myself in a very old paper, that we introduced these surfaces that were not in the literature. So these are all rotation surfaces in a certain sense. Okay, then I don't want to go into details of this proof because I want to talk about some applications of this theorem. Yeah. The first one, okay. The first application is a very curious property of R3. You see, I did these things in the product space of a surface of a constant Gaussian curvature with a fixed R. But R3 is also a Euclidean space with R. Yeah? So everything I've done in my theorem can be applied to Euclidean space. I just choose an arbitrary direction and take my R3 space as a plane perpendicular to the fixed direction with this R. And suppose that we have a compact surface in motion in R3 with H constant. Take a fixed direction R3. Suppose that this fixed direction is such that the following property is satisfied. Projection of L, a straight line which is parallel to sheet, projected on the surface is the principal direction. I take this as Z1, and the normal of this vector, Z2. I have a frame in the condition that I mentioned before, and this diagonalizes the second fundamental form of the surface. Then I can apply all I have done for my other space, and this would be a rotation surface, the canonical rotation surface of R3. But the rotation surface of the constant mean curvature are onduloids or nodoids, but the only compact one is a sphere. So it has to be a sphere. Just an application of the method that I used to prove the theorem. So it's a characterization of a sphere which can be described as a very strange characterization, because you are saying this. If there is a direction in 3 space, such that the projection on this compact surface is the principal direction, all directions are principal. There has to be a principal direction for every point. Then all directions there will be a sphere. A way to talk about this sphere that the compact umbilical surface, all directions are principal. Yeah. So there might be other ways of expressing that, but I find a very, very curious property of the sphere. The next, I want to make another application. Okay. The surface, I mentioned this Aberge-Rosenberg form, quadratic form, and we call Aberge-Rosenberg surface those for which this quadratic form vanishes, because they are the interesting thing. They form a very important class of surfaces in this product space. And if this form, the KZ2, can be written, that's another way of writing that KZ2. But that's it's the same way that we write the Hopf form from this expression, the real expression, the second fundamental form. That's the same way there, and that's okay. That's the way that's what the Rosenberg form is. It's the same form as I said before. And to be 0, we show easily, just looking, that alpha 1, 2 equals 0, and the difference of alpha 1, 1 minus alpha 2, 2 is just this k sinus squared theta over 2h. That alpha 1, 0, 0 is immediate, alpha 1, 2, because you see, this key of alpha 1, 2 is key E1, E2, E1, E2, and it should, to be 0, you have to have this quotient of I, key Q, E1, E2, 0. But that is, since she has no component of 2, she is E1 sinus theta plus E3 cosinus theta. So there is no component in 2. Then the inner product with E2 is 0, so the only way is that alpha E1, E2 is 0. That's more or less immediate from that equation. And then a little bit of computation so that the second equation is okay too. So they are all, so Aberge-Rosenberg surface, they are all rotation surfaces in that category that we are looking at. I mean, that's all known because that's the way it was found was to look at the parametrization of the rotation surface and starting these things and showing that the certain number of them satisfy the Abel-Rosenberg equation, and they were all. I mean, that's a long way to go. And I would like, from this point of view, to look at some qualitative properties, not to describe in detail, but have the forms of the surface. I mean, that sometimes all you use in your work is a qualitative property. So it's from the fact that we know the difference of alpha 1, 1 and alpha 2, 2, we can see that they have this expression described there. Note that alpha, if k is negative, alpha 2, 2 is always non-zero. Yeah. That's a very important point. Well, and then if we take the product of these things, since alpha 1, 2 is 0, this is the extrinsic curvature, Ka by Ka, so I'm saying extrinsic curvature. And this has this expression there. And we have two cases. And these two cases will include everything. First, 4H2 plus K sin squared, it is positive. From that we show that the numerator in Ke is positive, so the surface has a positive extrinsic curvature. And the second case, just the negative or zero case of this situation. Next, please. So, in case A, we know from recent paper by Rosenberg, Galvez, and Jose Maria Spinar. Spinar, Galvez, Rosenberg, to put in the correct order, that's a convex surface. Yeah. And then we have two situations. Either it's compact and has to meet the axis twice. The first way, because it's away from the axis, it will have a point of where it's not convex. And if it's compact, it meets once, it has to meet twice. And embedded in the homomorphic sphere. So it is one of these Rosenberg surfaces. It's called HS. Then now I can come back to one, the one right in the beginning. The one I said I would miss. Oh, you took that? Doesn't matter. Okay. This, yeah. So these are the descriptions. The average Rosenberg surfaces are either this compact one, which is SO42 as well known already in the literature, is a convex surface embedded. It's denoted by SH with the 2 to say just to a surface. Or it's a graph of a slice. A slice is just the cut of the ambient space by a fixed value of the axis. Is a graph with these things, or it's a catenoid-like surface. These trees are the one which have a real x. And there is the one which has a virtual x, which is actually, as you move the x to infinity, this catenoid type and this disk type approach. If you fix the x, they don't change. But if you move the x, they keep on changing. And in the limit, they become a surface called this is a surface foliated by Horo cycle. It's a curious thing, but it's going to be so. So that's what we find there. Now we come back again to the end. Okay. So, in case A, we were in the convex case, either compact or complete, non-compact. complete is just that type H, S, and the complete non-complete is the graph of a convex current of a slice. So it is EH. Well, if you know the term, you would ask, and there is another type, which is a special kind of end, which is foliated by Horace sphere and has a special end. It will not appear here because to have a foliation by Horace sphere, you must have a condition that will be in the next page, and I'll show you that does not, it cannot be compatible with being convex. No, that's not well. Anyway, well, case B. So we have this thing is minor or equal to 0. Since this alpha to 2 is always positive, we have two cases to consider. It's negative, 1, 1. Alpha 1 is negative, so it's not convex. It's a saddle surface. It's exactly the CH, at least qualitatively, or it is identically 0. Then a computation that is very curious computation. You take K, this curvature to the square, sum with the curvature of the ambient space, and this involves alpha 1, 1, alpha 2, 2, and you put them all with the condition that alpha 1 is 0, and make the computation becomes at 0. Yeah. Well, that's good, because this means that the absolute value of this curvature kg is equal to the root of k. It means that h, the sigma, that C curves were horocycle. That's precisely this condition that is a horocycle. See, the root has to appear because it's a square that's equal to k, not without the square, because one is a surface curvature, the other is a curvature. So it has to have this. They are not of the same dimension, physical dimension. So then it is this pH that we have. So they are all here. Yeah, all surfaces are in this. We call it in this case, and we have a simple way to distinguish them by just saying it's something is great positive or something is negative. Well, I guess I talked enough already. It's all I have to say.